Welcome to Module 17, Build a Small Network, the finale. This module doesn't introduce new concepts so much as it pulls together everything from all 16 prior modules, design, deployment, verification, and troubleshooting, into one cohesive picture. Frame it as the capstone. Students should recognize almost everything here from earlier in the course, just applied practically now. Objective: implement a network design for a small network including a router, switch, and end devices. Preview the long topic list on screen. Devices in a small network, applications/protocols, scaling, verifying connectivity, host iOS commands, troubleshooting methodology, and troubleshooting scenarios. This is a long module that reviews and applies the whole course. Most businesses are small, so most business networks are small too. Fewer device types, simpler topology than an enterprise network. The diagram shows the typical small network: one router to the internet, one switch, a WAP, wired PCs, an IP phone, a printer, a server, all usually on a single WAN connection via DSL, cable, or Ethernet. 4 factors balance when choosing intermediary devices. This slide covers the first 2, shown on screen. Cost, driven by capacity, port count/type, backplane speed, management features, embedded security, cable run expense, and speed/port types. Newer devices ship with 1 gigabit per second NICs. Some servers use 10 gigabits per second, faster. Layer 2 devices let the network evolve without a full replacement. The other 2 device selection factors shown on screen. Expandability. Fixed configuration devices can't grow. Modular devices have expansion slots. Switches especially benefit from add-on high-speed uplink ports and OS features/services. The device needs an OS supporting the org's actual requirements. Layer 3 switching, NAT, DHCP, security, QoS, VoIP. Every host and device needs a unique address, and planning a documented addressing scheme by device type massively simplifies troubleshooting. Walk the reference table on screen. Gateway, switches, access points, servers, printers, IP phones, wired devices, wireless devices, each with its own assignable range summarized to a specific subnet. This exact table is the kind of scheme a real admin would build and follow. Concrete worked example applying the scheme from the previous slide to 192.168.2.0/24. Default gateway at 0.1, switch at 0.5, server at 0.17, wired PC at 0.65, each landing exactly where the addressing plan predicted. Point out the tip on screen. Because ranges were deliberately allocated on subnet boundaries, adding a second switch at 0.6 still falls under the same summarized 192.168 by 0.4/30 block, no policy rewrite needed. Even small businesses depend heavily on their network, so a failure can be costly. Redundancy eliminates single points of failure through duplicate equipment or duplicate links for critical areas. The diagram shows 2 separate paths from a switch to the internet. If one link fails, traffic still has a way through. Good design enhances productivity and minimizes downtime, including managing real-time traffic like voice and video via QoS, classifying traffic by priority during congestion. Walk the table on screen. VoIP gets high priority, sent to backbone in priority order. SMTP gets medium priority, no special treatment. Instant messaging gets best effort, standard delivery, no guarantee. A network is only as useful as what runs on it. 2 categories, shown on screen. Network applications, software that communicates directly over the network and implements application layer protocols itself, email clients, web browsers, versus application layer services, programs that need help from application layer services for things like file transfer or print spooling, transparent to the user but essential underneath. Network administrators regularly need remote access to devices and servers. VACE, SSH is the secure alternative to Telnet, and once connected, admins work as though logged in locally. Both the network device, router, switch, AP, and any server being accessed need to actually support SSH server services for this to work. The fundamental toolset of a network professional, shown in the table. Web servers use HTTP, HTTPS. Email servers use SMTP, population 3, IMAP. FTP servers use FTP, SFTP. DHCP servers use DHCP. DNS servers use DNS. Point out the trend on screen. Many companies now require the secure versions wherever possible. SSH, SFTP, HTTPS. Businesses increasingly rely on IP telephony and streaming media, and remote employees need voice/video support alongside regular file and software access. Administrators have to ensure equipment and configuration guarantee priority delivery for this traffic, directly connecting back to the QoS discussion from slide 9. Growth is natural for small businesses, and networks have to scale with them, ideally with enough lead time for intelligent decisions rather than reactive scrambling. 4 elements drive scaling, shown on screen. network documentation, physical/logical topology, device inventory, budget, itemized IT equipment purchasing, and traffic analysis, documented protocols/applications/services and their requirements. As a network grows, understanding actual traffic flow matters. Protocol analyzers like Wireshark reveal what's really moving across key hosts. The mock-up on screen shows a protocol hierarchy view with percentage breakdowns by protocol: Ethernet, IPv4, TCP, HTTP, TLS. Exactly the kind of view an admin uses to understand where bandwidth is actually going. Beyond traffic trends, admins should track how network use itself is changing over time. Windows built-in tools, Task Manager, Event Viewer, Data Usage can capture OS version, CPU, RAM/drive utilization, and which applications, network and non-network, are running. The Data Usage tool specifically, Settings Network and Internet Data Usage, is great for spotting which apps are consuming the most bandwidth. Ping is the fastest Layer 3 connectivity test using ICMP Echo Request Type 8 and Echo Reply Type 0. On Windows, Ping sends 4 consecutive requests and expects full replies. Walk the sample output on screen, including round-trip time stats. This is the exact same ping mechanism covered in Module 13, now applied as a practical verification tool. Cisco iOS ping differs from Windows, sends 5 ICMP echoes by default, 1 character per reply. Walk the indicator table on screen, means a successful reply, validates Layer 3, connectivity, means a timeout, connectivity problem along the path, U means the router returned a destination unreachable message. Reading these symbols quickly is a core troubleshooting skill. Standard ping uses the closest interface to the destination as its source automatically. Extended ping, type ping with no destination in privileged exec mode, lets you customize the source address and other parameters. Walk the example on screen where R1 explicitly sources the ping from 192.168.10.1 instead of the default interface. Ping confirms a Layer 3 problem exists, but not where along the path it's happening. That's traceroute's job, listing every hop reached. Syntax differs by OS: traceroute on Windows, traceroute on iOS/Linux. Point out the tip on screen. Windows traceroute uses ICMP echo requests, while iOS/Linux traceroute uses UDP to an invalid port, relying on the destination's port, unreachable reply to signal completion. Same TTL incrementing mechanism from Module 13, different underlying protocol. Like extended ping, extended traceroute, type traceroute with no destination in privileged exec mode, lets an admin adjust parameters, useful for locating routing loops, determining the next hop router, or finding exactly where packets get dropped. Walk the example output on screen, including the asterisk marking a lost/unanswered probe on the final hop. A network baseline, built over time by capturing and archiving ping/trace output with timestamps, is one of the most effective monitoring and troubleshooting tools available. Measuring at varying times and loads gives a clearer performance picture. Watch especially for growing response times over successive baselines, a clear sign of developing latency issues. Checking host IP addressing is standard practice for verifying and troubleshooting connectivity. 4 key settings to check: address, mask, router, gateway, and DNS. Walk the IP config/all output on screen. Mention NSLookup as another useful DNS troubleshooting tool for manually placing queries and analyzing responses. On Linux, ifconfig, or the newer IP address command, shows interface status and IP config. On Mac OS, the same ifconfig command works from the terminal, alongside GUI access via network preferences. Walk both sample outputs on screen. Same underlying information as Windows IP config, different command and format. The ARP command lists everything in a host's ARP cache: IPv4 address, MAC address, and type, static/dynamic. Important caveat: the cache only shows recently contacted devices, so ping something first to populate an entry before checking. Mention netch interface IP delete ARP cache as the way to clear the cache if needed. May require admin rights. Reference table of the most useful show commands, worth having students keep handy. Show running config, current settings. Show interfaces, status and errors. Show IP interface, layer 3 info. Show ARP, known local hosts. Show IP route, routing table. Show protocols, which protocols are operational. Show version, memory/interfaces licenses. These pull together commands from throughout the entire course. CDP, Cisco Discovery Protocol, runs at the data link layer, so Cisco devices can discover each other even without layer 3 connectivity, revealing device ID, addresses, port IDs, capabilities, and platform for directly connected neighbors. Walk the sample output on screen. Important security note: disable CDP on user-facing ports specifically. No CDP run globally, or no CDP enable per interface. Show IP interface brief is one of the most frequently used commands, a condensed summary listing every interface, its assigned IP if any, and operational status. Walk the sample output on screen, pointing out the up/up versus down/down status combinations and what each means about the interface's actual state. Show version verifies and troubleshoots basic hardware/software components from the boot process, iOS version, uptime, configuration register, installed hardware, and interfaces. The tip on screen sums it up well. This command pulls together everything from this whole section into one quick sanity check before diving into deeper troubleshooting. The 6-step troubleshooting methodology, based on the scientific method shown on screen. Identify the problem. Talk with the user first, often the most useful step. Establish a theory of probable causes. Test the theory to determine the actual cause. Establish and implement a plan of action. Verify the solution and apply prevention. And document findings/actions/outcomes. This structured approach applies to any technical troubleshooting, not just networking. Not every problem gets resolved on the spot. Escalation makes sense when a fix requires manager approval, specialized expertise, or access the current technician doesn't have. Walk the example on screen. A technician determines a router module needs replacing, which needs manager approval, which might itself need financial sign-off before purchase. A clear company policy should define exactly when and how to escalate. The debug command shows real-time messages for troubleshooting, but use it sparingly, since debug output gets high CPU priority and can genuinely render a device unusable. Walk the example on screen. Debug EPI-CMP, then a ping showing the live debug trace, then turning it off with no debug EPI-CMP or undebug all. Specifically, avoid debug all and debug IP packet that generate enough output to overload a router. Debug output shows automatically on local console connections, but not on remote telnet/SSH sessions by default. Terminal monitor redirects those messages to the current remote session. Walk the example on screen. Connecting remotely, enabling debug, then terminal monitor to actually see the output. Use terminal no monitor to stop it when finished. Duplex is the direction of data transmission. Auto-negotiation lets connected devices agree on the best mode both support. Half duplex restricts communication to one direction at a time. Full duplex sends and receives simultaneously, the modern standard. If one side runs full and the other half, a duplex mismatch occurs. Data still flows, but performance is very poor. And this specific problem can be tricky to diagnose since it's not an outright failure. Since IP addresses are hierarchical, an assigned address must conform to its network's range. Wrong assignments cause conflicts and routing problems, often from manual mistakes or DHCP issues. Walk the verification approach on screen. Show IP interface, or Show IP interface brief on an iOS device, reveals exactly what's assigned to each interface, the first step in diagnosing addressing problems. When a Windows device can't reach a DHCP server, it self-assigns from the 169.254.0.0/16 range. APIPA, Automatic Private IP Addressing. A host with an APIPA address usually can't communicate at all, since no other device is on that address range. Important OS difference. Linux and Mac OS will not self-assign in this scenario. They simply won't get an address. Verify with ipconfig on Windows. Seeing an APIPA address in the output confirms the diagnosis immediately. The default gateway is the closest device that can forward traffic to other networks. An incorrect or missing gateway prevents communication with any remote network, and the gateway's address must be on the same network as the end device. Walk the Show IP route output on screen showing the gateway of last resort. This is the router side view confirming the gateway itself is properly configured. DNS resolution isn't strictly required for basic connectivity, but it's critical from the end user's perspective. When DNS fails, users often conclude, quote, "The internet is down," even though routing and every other service is working perfectly fine. Walk the public DNS provider table on screen. Google 8.8.8.8, 8.8.4.4, and Cisco OpenDNS 208.67.222.222, 208.67.220.220. OpenDNS specifically adds security filtering against phishing and malware sites. Course wrap-up. Walk each bullet as a genuine recap of the whole semester. Small network design, topology, device selection, addressing, redundancy, traffic management, applications and protocols including voice/video, scaling considerations, ping/traceroute verification, standard and extended, host, iOS commands for gathering information, the structured 6-step troubleshooting methodology, and the most common real-world connectivity issues. This is the moment to remind students how far they've come, from Module 1's basic networking concepts to now being able to design, build, verify, and troubleshoot a real small network end-to-end.